In this video, we're going to introduce you to the very important concept of the equilibrium constant. To show you what an equilibrium constant is, let's talk about a chemical reaction. Let's illustrate this looking at the chemical reaction where 1 mole of dinitrogen tetroxide decomposes to form 2 moles of nitrogen dioxide. So if we wanted to, let's say we performed an experiment, or actually 5 different experiments, and we start with different concentrations of our reactant and product. Here you can see in the first experiment, we're starting with 0.04 molar reactant and none of our product. The second one, we're starting with 0.08 molar product and none of our reactant. And then in 3, 4, and 5, we have varying concentrations of reactant and product. So these are just chosen at random, no special reason for these. But so we start with some initial concentrations of reactant and product, and let's say we let that reaction occur. Eventually this reaction will reach equilibrium. And of course at equilibrium, the concentration of the product and reactants remains constant. So let's let this reaction run, and when it does, we measure the concentrations of product and reactant at equilibrium. And we get these values. The important point, or where the equilibrium constant comes in, is if we look at the ratio of product to reactant using the equilibrium concentrations. More specifically, if we take the concentration of NO2, our product, squared, and we're squaring it, as we'll see, because we have a 2 coefficient here, and we divide it by the concentration, the equilibrium concentration of the reactant, for all of these experiments, we get the same value. This value is what's called the equilibrium constant, and this ratio of product to reactant is what's called the equilibrium constant expression. So again, our equilibrium constant expression for this particular experiment is the concentration of product raised to whatever molar coefficient is in front of that product, in this case a 2. So we take the concentration of NO2 squared, and again the equilibrium concentration, not initial, and we divide it by the concentration, the equilibrium concentration of our reactant. So if we plug in any of our data, let's look at experiment 1. If we plug in this data into our equilibrium constant expression and solve, we get a equilibrium constant value of 4.64 times 10 to the minus 3. If we take that same equilibrium constant expression and we plug in the equilibrium concentrations from experiment 5, of course those are different than experiment 1, but when we plug it in, we get the same constant. So we can make a general statement about equilibrium constants and equilibrium constant expressions. If we look at this, this generic equation, A moles of A plus B moles of B reacts to form C moles of C and D moles of D. So whatever is written on the right, we define as the products. Whatever is written on the left, of course, we define as the reactants. So we could write an equilibrium constant expression for this reaction by taking the concentration, the equilibrium concentrations of my products raised to whatever molar coefficient is in front of them, you can see that here, divided by the equilibrium concentrations of the reactants raised to whatever molar coefficient is in front of them. That will give you what we call the equilibrium constant. We'll talk more about what that, what information we can get and why equilibrium constants are so important more in just a little bit. So just to review, the reaction we just looked at here, if we wanted to write an equilibrium expression for it, we would take the product, the equilibrium concentration of product, squared, since we have a 2 here, and we would divide that by the equilibrium concentration of my reactant. Then we could plug in whatever equilibrium concentrations we get for this reaction, and we'll come up with the same value called our equilibrium constant. Now, it is important to note that the equilibrium constant does depend on temperature. So as long as we keep the temperature constant for a given reaction, it doesn't matter what concentrations you have at equilibrium, you'll always get the same Kc value. If you change the temperature, then the Kc value for that reaction will change. So let's practice writing some equilibrium constant expressions using the following three chemical equations. So pause the video, see if you can write an equilibrium constant expression for each of these, and then we'll go over them. Okay, so let's take a look at the equilibrium constant expression for each of these. For the first one, the equilibrium constant expression will be the concentration of product ammonia to the second power divided by the equilibrium concentrations of my reactants, N2 to the first and H2 to the third power. For the second one, the equilibrium constant expression will be the equilibrium concentration of my products, PCl3 to the first, Cl2 to the first, divided by the equilibrium concentration of my reactant, PCl5 to the first. For the third one, the equilibrium constant expression will again be the equilibrium concentrations of my reactant raised to their coefficient, CO2 to the first, CO, carbon monoxide to the first, and equilibrium concentration of H2 to the third, divided by the equilibrium concentration of reactants, methane to the first, and water to the first power. Now, in these, we could plug in any equilibrium concentrations, and we would get a constant value for Kc as long as we kept the temperature constant. So let's practice a few more of these equilibrium constant expressions. If you would, pause this and write the equilibrium constant expression for these three. And notice that, again, the second equation is the reverse of the first, and the third equation is the first. However, we have doubled all the molar coefficients. Okay? So take a minute and write those expressions. Okay. So the equilibrium constant expressions would be as follows. You could see for the first one be ammonia squared divided by the concentration of nitrogen times the concentration of hydrogen cubed. The equilibrium constant Kc expression for the second one would be the products, in this case what's on the right, nitrogen to the first times the concentration of hydrogen, equilibrium concentration cubed, divided by the equilibrium concentration of ammonia squared. And the final one would be the concentration of ammonia at equilibrium to the fourth power, divided by the equilibrium concentration of nitrogen squared times the equilibrium concentration of hydrogen to the sixth. Now, one thing I want to point out about this is the relationship between the Kc values. If this is we'll call this Kc, since this one is the reverse of the first reaction, the Kc value for the second equation is related to the Kc of the first, as we see here. The Kc for the second one is 1 divided by the Kc of the first. So if you reverse a reaction, the Kc value for that reverse reaction would be the inverse of the Kc value for the first reaction. For the third reaction, we have doubled all the coefficients when compared to the first. So the Kc value for the third one would be the Kc of the first reaction squared. So when you double the coefficients in a reaction, the Kc value is the square of the reaction where you didn't double the coefficients. So it's important to appreciate the relationship between Kc values if you reverse a reaction or if you double the coefficients. So let's try one more. Write the Kc expression for these two reactions, and then show how the equilibrium constant for the first is related to the equilibrium constant for the second reaction. So pause the video and try that. Okay. So, of course, the Kc expression for the first would be the product squared divided by the concentration of SO2 squared times the concentration of O2 to the first. It doesn't matter what order you write those in. And of course, these are equilibrium concentrations here. The Kc expression for the second reaction would again be the product SO2 squared, the concentration of that, times the concentration of O2 at equilibrium to the first, divided by the equilibrium concentration of SO3 squared. The equilibrium constant for the second reaction is going to be the inverse of the equilibrium for the first reaction. Since this is the reverse, the Kc values would be, for the second, would be the inverse of the first. So what information can we get from our equilibrium constant? Well, the magnitude of the equilibrium constant can tell us a lot about which direction the reaction proceeds. Do you get a lot of product or a lot of reactant once the reaction has reached equilibrium? So a large equilibrium constant, generally 1,000 or more, indicates that at equilibrium, the concentration of product is much larger than the equilibrium concentration of reactant. So for this reaction where A and B are at equilibrium, hence the double arrows here, if we wrote a Kc expression for this, it would be the equilibrium concentration of B over A. If you have a high concentration of B at equilibrium and a relatively low concentration of A, then your equilibrium constant will be large. So that can tell us that once a reaction reaches equilibrium, there'll be a lot more product than reactant. Now conversely, if you have a very small equilibrium constant, maybe a thousandth or less, so 10 to the minus 3 or less, that indicates that your equilibrium concentration of reactant is going to be relatively large when compared to the equilibrium concentration of your product. So if this reaction were to reach equilibrium and you had a very small Kc value, that would mean that the reaction did not proceed very much, so you still have a lot of A relative to the equilibrium concentration of B, giving you a relatively small Kc value. So the smaller the Kc value, the less the reaction proceeds from left to right. And finally, if you have an equilibrium constant that's between 10 to the third and 10 to the minus third, that indicates that at equilibrium you have an appreciable concentration of both product and reactant. So the reaction, the concentration of these two, you have a significant concentration of both once you reach equilibrium. And one last thing about the equilibrium constant, let's look at it in just a little bit more detail and show how it is actually derived. And to do that, we need to think back to our kinetics. So let's say that we have this elementary reaction, elementary meaning that it occurs in only one step, where A plus B is in equilibrium with C plus D. Since the forward and reverse reactions are occurring, we could write a rate law for the forward reaction. Remember that a rate law is rate is equal to the rate constant, here Kf for the forward reaction, times the concentration of reactants, concentration of A, concentration of B. If we're talking about the reverse reaction, now these C and D would be considered my reactants. So for the reverse reaction, these are my reactants, C and D. A and B would be considered the products. So I could write a rate law for the reverse reaction. The rate of the reverse reaction is equal to a rate constant, we'll call that Kr for the reverse reaction, times the concentration of products, in this case Cd for the reverse reaction. So we have our two rate laws for the forward and reverse reaction, and we also know that at equilibrium, the forward and reverse reaction rates are equal. So the rate of the forward and reverse reactions are equal. That's the definition of equilibrium. So we can set these two rate laws equal to each other, as I have here. The rate of the rate of the forward reaction has been set equal to the rate of the reverse reaction. Now, using a little bit of algebra, we can move our rate constants to the same side and our concentrations to the other side. And when we do that, we get something that begins to look like an equilibrium constant expression. So this would be considered the equilibrium constant expression. And we have our rate constants, Kf and Kr, on one side. These rate constants, the ratio of the rate constant for the forward and reverse reaction, is what we call our equilibrium constant. So the equilibrium constant is really the ratio of the rate constant for the forward reaction divided by the rate constant for the reverse reaction. So if you have a Kc value, a rate constant that, equilibrium constant that's very large. Remember what that means. An equilibrium constant that is large means that you have a lot of product relative to the reactant at equilibrium. The reason for that is because the rate of the forward reaction is much faster than the rate of the reverse reaction. So if you have a large Kc, then the rate constant, therefore the rate of the forward reaction, is much larger than the rate constant, and therefore the rate of the reverse reaction. So that gives you a high buildup of product relative to reactants. Conversely, if Kc is very small, that means that the rate of the reverse reaction is occurring much faster than the rate of the forward reaction, as seen by the large rate constant for the reverse and the small rate constant for the forward reaction. That means that you'll have a higher concentration of reactant relative to product once the reaction has reached equilibrium. So be sure to appreciate what the rate constant is, how to write a rate constant expression, what it means, the magnitude of the equilibrium constant, and then also appreciate how the equilibrium constant is derived using the rate laws.